Welcome to lecture 7. We are still doing chemical kinetics, and we discussed elementary reactions, but as I have told you several times that lots of reactions happen when you put fuel and oxidizer together, very large number of reactions, and we have to see how we analyze sets of reactions occurring together or one after the other or happening simultaneously, things like that. So, in this context we will discuss how to analyze complex reactions. Now, three examples of complex reactions are opposing reactions, then concurrent reactions, and also consecutive reactions. And we will discuss all this from a very simplified point of view, in the sense that we will take examples where the species are just written as A, B, C, so symbolic, and some of what I will write will appear to be simplistic, not very common. So, let us say we have reactions A giving you B and also B giving you A. So, this is an example of opposing reactions. We can also have concurrent reactions. So, that will be A giving you B and A also giving you C at the same time. So, these are happening simultaneously. Then you can also have consecutive reactions. So, that is like A giving you B, and what does consecutive mean? What should give you C? Yes, that is correct. So, this is a consecutive. Consecutive means one after the other. So, A gives you B, B gives you C, and this K1 and K2, these are reaction rate constants. Now, in today's class at least, we will look at A, B and C without really specifying what these are. Now, you will also recognize that reactions are most likely bimolecular or even termolecular, but here we seem to see just one species giving some other species. Okay. So, this is an extremely simplified version, but we are looking at this simplified version because this will help us understand, help us analyze some of these complex reactions. So, these are more complex than what we had analyzed till last class. So, these are happening with one reaction depending on the other in some way. Okay. Now, what do I mean by analyzing? What do we want to find out? We want to find out, let us say, how the concentration of A changes with time, how concentration of B changes with time, how concentration of C changes with time, things like that. And we did some of that in the last class, wasn't it? Zeroth order reaction, first order reaction, second order reaction. We wrote expressions for concentrations in terms of time. So, we will do something similar, but since now we have these sets of reactions happening, we will be able to figure out certain new aspects of these reactions happening together. So, let us first look at opposing reactions. So, for opposing reactions, we just wrote A giving you B, and we have this double headed arrow. So, that means this A goes to B with a reaction rate constant K1 and B goes to A with a reaction rate constant K2. Again, what are we interested in? We are interested in writing expressions like this. So, is this correct? dA dt is minus K1A, dB dt is K1A, is that correct? No, because we need to write something else also. So, for dA dt, it should be minus K1A plus K2B. and for dB dt we have written k1a, that is correct, but we should write minus k2b. Now, let us also say that the initial concentration of A is A naught and the initial concentration of B is 0. So, again what are we trying to do? We will try to get these concentrations of A and B as function of time. And in this particular case, since we are talking about opposing reactions, something interesting will happen that you can probably visualize even now. That after a while we should expect to see some sort of an equilibrium, because A is going to B and B is also going to A. After a while the rates will be such that the concentrations should not change. I think we can see that, isn't it, even before doing any kind of analysis. So, we will look at writing expressions for concentrations, but also keep in mind that we have a special case here when equilibrium will be reached, and then try to do some analysis pertaining to equilibrium. So, let us say that at time t equal to t, that is some general time, we have concentration of B equal to x, and then concentration of A should be A naught minus x, because every time a reaction takes place A gets consumed and then from the initial A naught it should reduce by some extent. So, if there is x concentration of B, then concentration of A should also fall by the same amount. So, it will become A naught minus x. Now, we have written an expression for dB dt. So, that means we can write an expression for dx dt. B is x. So, just a few minutes back we wrote dB dt. So, dx dt should be taken from dB dt and it should look like this. What is this? A naught minus x, that is A. So, k1a minus k2b, that is what we wrote few minutes back. So, this should be correct. And we will try to also write an expression for the situation when there is equilibrium. So, there will be equilibrium. So, at equilibrium dx dt should be equal to 0 and x will reach a certain value which we call x e. So, based on that we can say that this will happen. So, this is from equilibrium, because we set dx dt equal to 0, and what I have just now done is write an expression for k2 in terms of k1. In terms of k1, but it also has x e, which is the equilibrium concentration of B. Now, remember that we often try to integrate equations to get functional dependence on time. So, we have this dx dt expression which was k1 and here we can use K2 from the expression that we just now derived. K2 is K1 times A naught minus Xc divided by Xe. If we do that, then everything will be in terms of K1. So, we got K2 in terms of K1, and we replace this K2 by the expression that we have already got in terms of K1, and then we will get dx dt in terms of K1 only and not K2. That is your dx dt. So, it has only K1, it does not have K2. So, this can be integrated, and if you integrate this, you will get I think you can just mentally try to verify whether this is possible, but should we get a log if we integrate this? We should, because we got dx dt here and we got xc minus x here. So, imagine dividing dx by this xc minus x and then integrating, then you should get log of some quantity which has xc minus x. So, that is understandable. And should you get a linear variation with time? We should, because if you take this dt from here, imagine that coming on this side, then you integrate, then we should be able to get this. Now, once you integrate, we get a constant of integration. So, where has that gone? We can take care of that, is not it? We can take care of that because we know the initial condition for x at t equal to 0, that is at the beginning of time, you had just concentration of A. There was only A, and then the reaction started. A started giving you B, and B also went back and started giving you A. So, all this kept on happening. So, that is why it is A going to B and B coming back to A. But initially at t equal to 0, x was 0. So, that condition has been used to get this. So, that is why the constant is gone. So, you have to check this out later. I think that is something which you can figure out, but do it at home. From here to here, the constant of integration has disappeared because we have used the initial condition. So, you should verify this result. I am not doing that intermediate step. So, this has to be done at home, and we can understand something from here, that if you plot, let us say, log of xc minus x, which is the left hand side, and if you plot that as a function of time, okay. So, this thing in red circle, if you plot this on the y axis, and if you have time on the x axis, then from the slope you can get this other quantity in red. So, we will get this. You know the initial concentration, and maybe you have also measured Xe, that is the equilibrium concentration. So, that will give you K1. All right. So, I am actually saying that if you are doing an experiment and if you are measuring x as a function of time, then you will get two things. You will know x as a function of time, and you will also know the final equilibrium concentration of x. So, you will have Xe. So, I am talking about how to use this expression which we have got after integration. Let us have this box here. This is what we got after integration. In which way can we think of using this? We can imagine that we are doing an experiment in which we are measuring x as a function of time. So, in that case, we will know the left hand side because we have x at all values of t, and we also have the final value of x, which is x e, because it reaches equilibrium. We know A going to B, B going back to A. In this process, there is an equilibrium reached. We can imagine that happening. That shouldn't trouble us in imagining, because that's something which you will expect. So you can get the left hand side, this circle here, you can get this quantity and plot that on the y axis as a function of time. As a function of time. So if you do that, in fact, from the slope you can determine k1. So we can get k1 from the slope. So that's one way of thinking about this equation in the black box, correct? What's the other way of thinking about it? The other way of thinking about it is that you already know k1 and you have from some source, maybe the value of x e, maybe you measured it or somebody has told you something like that. Then this equation in the box will give you x as a function of time. So it will give you concentration of B as a function of time. So that was one of our objectives. We wanted to see how concentrations change with x. Now if you get the concentration of B as a function of time, do you also get the concentration of A as a function of time? What do you think? Is it easy to get that? Yes, because concentration of A is nothing but A naught minus x, which is the concentration of B. So you can get that too. So you got all the concentrations, both the concentrations as function of time. But in this case, I also give you this other interpretation that you can maybe think of this equation in the black box, which you just now wrote down, that okay, maybe I don't have x, I'm not looking for, maybe I don't have the value of k1, and ultimately maybe our objective is to get k1. So I'm changing the perspective. I'm saying that okay, maybe I don't have k1. If I don't have k1, maybe this equation on the box, in the box, can be used to plot this log quantity on the y axis and time on the x axis, and from the slope you can get k1. Okay. Now at combustion engineers, we will not be doing this sort of stuff. It's typically not our job to get the reaction rate constants, but there are some combustion engineers who are more focused into chemical kinetics, and they are more into determining rate constants of equations. Not a usual thing that we will think of doing in this course, but this is possible. So we can get k1. If you get k1 from this slope, can we also get k2? Yes, because we had this expression, that other box, not box actually, the other expression on the last slide, this one here. So that gave us k2. So you got k1 and k2. Okay. So this sort of experiment can give us the reaction rate constants. Now there's one more thing. Since it's equilibrium, there's one more aspect that we can think of. There is an equilibrium constant which we can define, which is B at equilibrium divided by A at equilibrium. What is our reaction? Our reaction is, set of reactions is A going to B, B going to A. That's what we are talking about. So an equilibrium constant can be defined as concentration of B at equilibrium divided by concentration of A at equilibrium. Again, this is something which you know from chemistry. Okay. Now you can prompt me here, what is B at equilibrium in terms of other notations that we had? Xe. Okay. And what is A at equilibrium? Yeah, I think I have less space here, but let me still try to write it. A naught minus Xe. A naught minus Xe. So let's write this out here once more for the sake of clarity. B at equilibrium divided by A of equilibrium, Xe divided by A naught minus Xe. And some time back we also had this. We had this. So, if you look at the first equation here, expression for equilibrium constant, and if you also look at this, compare the two, you can say that Kc is what in terms of K1 and K2? K1 by K2. So, this is an important result, and equilibrium constant can be expressed in terms of reaction rate constants. And if you know K1, for example, suppose you have done some experiments to get K1, then you can use the equilibrium constant to calculate K2. Okay. Who will give you that equilibrium constant? Equilibrium constant can be obtained using just thermodynamics, correct? We had looked at that few classes back. Does anybody remember that? In terms of standard state Gibbs function change, isn't it? We wrote that as a Kp, I think, but Kp and Kc are related. Kp was in terms of partial pressures and Kc is in terms of concentrations, C for concentrations, but these two can be related. So, equilibrium constant can be calculated purely based on thermodynamics. So, that is a good thing. So, that means that if you have K1, since Kc is equal to K1 by K2, suppose you have K1, somebody has given you K1 or you have made some measurements which gives you K1, then getting Kc is easy because that is just picking up thermodynamic data. So, you can calculate K2. So, this is a means of getting a reaction rate constant. Okay. Again, we will not be doing so much of this sort of analysis in the rest of the course, but still this is a good thing to know. Now, the other two types of complex reactions that I mentioned are concurrent reactions and consecutive reactions. The concurrent reactions concurrent means happening simultaneously at the same time. So, A going to B, I said, and then A going to C through K1 and K2. Now, I am writing a single headed arrow. So, I am not considering B going back to A and C going back to A. So, it is just this. And here let us just try to write this quickly. What is minus dA dt? Let us treat this as an exercise for you to practice writing expressions like rates of reaction. So, minus dA dt is the rate of reaction, that sort of thing. So, what do I write for this? Minus dA dt, K1 A from the first equation and K2 A from the second equation. So, that is good. And what about dB dt, K1 into A, and dC dt is again very similar, it is K2 into A. Again note that we are dealing with concurrent reactions. So, there are two reactions happening at the same time, but each of these reactions has been kept very simple. So, A going to B, just A going to B. It is not like X plus Y giving you P plus Q, that would have been a bimolecular reaction. So, it is not even that, it is just simple A going to B. I am not even saying what is A, what is B, we are just at a conceptual level, we are just trying to see how concentrations change as functions of time. So, this is okay. Now, you will see that it is very easy to meet one of our objectives. We can do that very quickly. What is concentration of A now? Can we integrate this and get concentration of A? let the initial concentration of A be A naught as before. So, we use similar notations as in the previous example. At t equal to 0, let us say A is just A naught and there is no B, there is no C at time t equal to 0. Okay. No B at time t equal to 0 and no C at time t equal to 0. So, what is A now? A will be A naught into e to the power minus k1 plus k2 into t. So, that is very easy to see. Okay. So, that means that A will decay, concentration of A will decay exponentially. So, that is good. It is easy to get, but getting concentrations of B and C will take some more effort. It is not going to be that straightforward, because if you replace the expression for A into in here in the dBdt expression, then you can integrate and things like that. So, you can get concentration of B, no doubt, but it will take you some more effort. It is not going to come in a very straightforward fashion. So, this will require some effort. Now, what I recommend is that you do this at home. Fine. So, that means we got concentration of A as a function of time. We would also like to get concentration of B as a function of time and concentration of C as a function of time. But in class, to save time, we will I will just give you expressions for B and C. So, after integration we will get B, concentration of B and concentration of C is expectedly something which looks similar. The expressions should look similar, right? Why should they look similar? Because A goes to B, A also goes to C. There is nothing much to choose between B and C. A going to B, A going to C, similar reactions. A goes to B through K1, A goes to C through K2. So, that is the kind of change that you will see here. It is like this part is the same in both, and B has this K1 here and C has the K2 here. So, that is expected. And you can also see that we can think of a limit t goes to t going to infinity. If t goes to infinity, the concentration of B will tend towards this and the concentration of C will tend towards this one. So, that is A, B and C.
T tends to infinity, is it equilibrium condition?
No, it is not equilibrium, it is reaching this sort of a terminal value, that is all. Okay. Equilibrium, we are talking about equilibrium in the sense that okay, A going to B and B going to A and the rates becoming equal. This is sort of reaching values in a limit. Okay. When actually this is better explained if you look at this plot. I think this is the same situation, A going to B, A going to C, and it is essentially those equations. What you see here on the plot are these curves for A, B and C based on the equations which you have just now written down, same thing. this is variation of concentration with time. A, B and C. A will have an exponential decay, we saw that, and B and C will actually rise with time because there is no other option. B is getting produced, C is also getting produced, they are not getting consumed by anything. So, B will build up, C will also build up. So, it is not equilibrium, but over a period of time, if you look at very long periods of time, then these curves for B and C tend to level off. They do not increase so much after a certain length of time, that is expected. We are talking about 1 minus exponential of minus k1 plus k2 into t, that sort of thing. So, that is the effect which you see here. That is concurrent reactions.
So, the variation is coming due to equilibrium concentration B and C.
Concentration of do you mean to say okay, the question is that I think the question is why B and C are different, is that the question? Yeah. So, the question is that you have concentration of B with varying with time, you have concentration of C varying with time. So, how is it that A going to B and A going to C, these are similar reactions, but why is it that concentration of B and concentration of C are not the same at all times? So, what is the answer to that? K1 and K2, because K1 and K2 are not the same, and if you take the ratio of I think we went out of focus maybe, yeah. So, here these were the two expressions for B and C, and you can see that ratio of concentration of B to the concentration of C is K1 by K2, okay. And the plot that I have just now shown you you need some values in order to be able to plot, and these this was done by assuming K1 by K2 equal to 2, K1 equal to 2 times K2, that was assumed to plot this. You need some values. So, since K1 is more than K2, you see B values to be higher than C values. Okay, so these are concurrent reactions. Now,
The equilibrium concentration can be much lesser than that T infinity concentration.
yeah, actually we are not even talking about equilibrium here, because these are irreversible reactions, A going to B and A going to C. Okay. Equilibrium discussion was valid in the context of the previous example, because A was going to B and B was coming back to A. There is no reverse equations taking place here. Actually, strictly speaking, you cannot really have only A going to B and A going to C without also having some extent of B going to A and C going to A. Okay, so there is a little bit of idealization involved. We are saying when I am writing A going to B with a single headed arrow, I actually mean that A going to B is very predominant, B going back to A is not very high, it is negligible. Okay. Now, we will do one more, and that will take us a little bit of time. That is in fact an interesting case. We are talking about, we will now talk about consecutive reactions. Happens to be quite interesting. So, here it is A going to B, and as you could guess that I should write B here. This set A going to B and B going to C is a set of consecutive reactions. So, again, what is the purpose of analyzing all this? We want to get concentrations as functions of time, and then just see what happens. Are there some interesting cases? So, dA dt is minus K1 and dB dt.
K1 into A minus K2 into E.
By the way, do you all understand why we are writing A in square brackets and B in square brackets? These are concentrations. So, kilomole per meter cubed, or maybe gram mole per cubic centimeter, units like this. So, number of moles per unit volume is concentration. So, that is what writing square brackets is like. So, we got a dC dt also. What is that? K2 into B. Again, easy to see what will happen to A, exponential decay, right. So, this should give us A equal to A naught into, what should I write? Minus K1 T. So, that is the exponential decay thing, that is straightforward. But like in the previous case, now to get B and C we have to do more work. It is not as straightforward as this one. So, you have to use this here and then integrate and things like that. So, you got, let us say in this equation we got dB dt, but you also on the right hand side you have got concentration of B, and this sort of thing requires more effort. This has to be done by you. Okay. So, what I am saying is that I will directly write the final expression, but we need to be able to work this out at home. So, that is concentration of B. So, these are B and C. Please verify at home, not here. It will take too much time here. And we will look at again some plots. This is concentrations as a function of time, and for these consecutive first order reactions, these reactions are all first order reactions, consecutive first order reactions, A going to B, B going to C, and there are K1 and K2. This plot again has meaning only if you choose some ratio of K1 and K2. So, in this case K2 is 2 times K1. For this plot K2 is 2 times K1. And you can try to interpret the concentrations A going down with time exponentially. because we wrote a naught a equal to a naught e to the power minus k1 t. So, that is happening. The decay of a with time, and concentration of B increases first and then it comes down. So, not so straightforward to interpret. Okay. And concentration of C overall keeps going up. That is expected, because A is going to B, but B is going to C. So, B is the tricky thing, because B is getting produced, but also getting consumed. So, you see this trend of B going up and then coming down, but we know that A should come down and C should go up. We expect that, because C is not getting consumed, C is getting only produced. The rate of production of C with time may vary in a complex fashion, and that is what is happening. You see that the rate is something here, more like linear, that it increases faster, then it comes down a bit, things like that. But B is more complicated, we can see that here. Remember that K2 equal to 2 K1 for this plot. Now, interesting things start happening if you plot the same set of equations for another case. So, in this case K2 is 200 times K1. Same plot, K2 is 200 times K1. Again, I can give you the plots at the end of the class. In any case, this lecture is being recorded, so you can take a look at these later. Right now, just please appreciate just the nature of these plots. Let's look at all the concentrations again. C is building up, C is growing, isn't it? C, in fact, in concentration of C first increases little slowly, then it picks up and then becomes almost linear. Concentration of B picks up and then it kind of levels off and it reaches some kind of a steady value. Concentration of A appears to be static, appears not to be changing, but it must be changing, right? Is it changing? It's changing. It's difficult to make out, but it's in fact changing, but slowly. It has an exponential decay. It has an exponential decay, but you can interpret it in this way. How does it change? It's supposed to be concentration of A is supposed to be A naught e to the power minus K1 t. We wrote that. So, in this case K1 is small and K2 is large, because we assumed K2 by K1 to be 200. So, we can interpret it this in this fashion, that K1 is small and K2 is large. If K1 is small, A will decay, but it decays slowly. In fact, in this particular plot it decays so slowly that you almost can't make out, it is almost leveling off. And you will also notice another thing on the plot, that concentration of B is multiplied by 50 and then plotted. So, the legend on the top of the dashed curve in the plot that you just now saw says 15 to B. What that means is concentration of B is typically very small in this case. It is so small that it has to be multiplied by 50 so that it shows up on the plot. Otherwise, it would not have shown up, it would have been hiding at the x axis, it would have been almost like 0 concentration. So, that is why it has been multiplied by 50 and then plotted. So, in this case we see that the concentration of B, first of all, it is small. So, we are talking about K2 much greater than K1, K2 equal to 200 K1. So, concentration of B is small in this case. It was not so small in the last plot. In the last plot that we talked about, B went up and then it came down. It had small values, but not as small as this one, because we did not have to multiply it by 50 or some such number in the previous plot. Okay. So, very quickly, this is what we had last time, isn't it? Last plot, this is for which case what values did we choose for K2 equal to 2 K1? This is the one which we had. So, the concentration of B was still okay, not very, very small, and it went up and then it decayed. It decayed as a function of time, keeps on decreasing, maybe slowly towards the end, but it keeps on decreasing. Whereas, in this case, concentration of B is really small. So, K1 is very small, K2 is much larger in comparison. So, this gives you very small values of B. So, that is one observation. The other observation is regarding B is the concentration of B is leveling off. It reaches a certain value. So, it reaches some kind of a steady state. It does not seem to change after that. This is not equilibrium, because again we are not talking about reverse reactions and things like that, but concentration of B, number one, it remains small, number two, it appears to achieve some kind of a steady state. Okay. Is C achieving a steady state? No, no, C is not achieving a steady state, but we can kind of, from if this plot is an indication, this tells you that concentration of C increases almost linearly. Mind you, concentration of C is also small in the sense that it has to be again multiplied by 50 here, but it is bigger than B, much bigger than B, and it keeps on rising. Concentration of C is not more than concentration of A. It is 50 times concentration of C which is crossing the A curve, and A is almost stationary. So, that is what is happening when K2 is much larger than K1. Just to acknowledge where these plots come from, these plots come from a book called titled Chemical Kinetics, a Modern Survey of Reactions by Nicholas, Nicholas, J. Nicholas. So, we will remember this, and then let us see what we can say now. We understood that if you have consecutive reactions and if the first reaction is slow, so A going to B is slow, B going to C is fast, then the concentration of B probably can be predicted by some steady state approximation, because it reaches a steady state. Okay. That is what we understand. So, we will have a dB dt term if we write the equations. We already wrote a dB dt term, we got an expression for B. So, dB dt can be set equal to 0, and from that we can get a concentration of B which corresponds to a steady state. So, what we have just now seen based on these two plots is that if you have the second reaction much larger than the going at a much larger rate than the first reaction, that is, the first reaction is very slow, in comparison the second reaction is rapid. If that happens, then the concentration of B reaches a steady state. Okay. So, this can be utilized. This can be utilized because sometimes we have sets of reactions in which the first is slow and the second is fast, and B is kind of like an intermediate. Why do I call it an intermediate? Because our reactant is A and our product is C. A is going to C through this intermediate B, and this intermediate is in small concentration reaching a steady state. Okay. So, if we want to know if you want to know the concentration of B, since it is an intermediate, since it is in small concentration, it is sometimes difficult to measure those concentrations. Concentration of B is very small, it had to be multiplied by 50. So, measuring that is hard. Since measuring that is hard, we sometimes do a theory which is the steady state theory. So, how will we do the steady state theory? We will set dB dt equal to 0 and then get an expression for B. Okay. We can do the steady state theory to get the concentration of B. Now, to make this slightly more interesting, we should step out of this ABC business for a while, for a few minutes.
You are saying that
A to B is slow and
Hmm.
B to C is fast.
Hmm. Hmm.
Then it will reach the B at steady state.
Yeah,
So
that is what we saw in the last plot. So it's by steady state I mean that it's leveling off, it's not changing with time. But remember, it has to be K2 has to be substantially larger than K1. Okay, for this to happen, because it didn't happen in this case. In this case, the concentration of B kept on decreasing. Okay.
so then why should there be any concentration of B at all? Because the moment it gets created, immediately it has to be get consumed into C.
Yeah. So the reason there is that A goes to B, so B is getting produced at a certain rate, which is dependent on the reaction rate constant of the first one. So it's dependent more on K1, the production of B. But the consumption of B is dependent on K2, which is the second reaction rate constant. So these two are not equal. See, since these two are not equal, it reaches some kind of a steady state. Okay. And the point is that also think about it this way, that initially we had only A, and then initially there is no B to C reaction. So initially B had a chance to develop. You see this here? B had a chance to develop. Okay. The second reaction is still slow, because the second reaction, the rate of the second reaction depends on K2, but it also depends on the concentration of B. Okay, so B is building up. So still the second reaction cannot consume B that fast. So B builds up, it reaches a certain stage. After that, okay, B is getting produced and getting quickly consumed. So it remains slow and it reaches a steady state. I think that's what your question is.
But sir, the consumption rate of B in the second reaction, after some time, after T the consumption rate of B in the second reaction is much higher than the production rate of B in the first reaction. So it should always decrease after some time. Why is it going in a steady state condition?
Yeah, that's kind of I think one way of maybe looking at this. Maybe let's see, maybe we can look at it from the equation point of view, and one way can be that we have the B concentration of B, we have the concentration of B, and we should try to plot this and see what happens if K2 is 200 times K1. Okay. And the trick will be to calculate these two terms separately. So we have this first term here and the second term here, and see. So B is actually this term minus this term. So what you can do is plot this term as a function of time, and plot the other term also as a function of time, and see initially how big is this term, initially how big is the other term, and after a while what happens to the relative magnitudes of these two terms. Okay, that's possibly one way of interpreting this.
So the one thing is because once B gets built up and then get consumed into C at a very fast rate, then the concentration of B also goes down.
Now concentration of B is
goes down, then that rate of reaction of this C will also go down, because dc dt is dependent on K2 as well as on B.
Yeah. So what I was actually telling you is that in this case, if you have K2 equal to 200 times K1, the concentration of B remains small, okay, but it's not decreasing with time. So if since this is not decreasing with time, concentration of C in fact keeps on increasing as a function of time. So concentration of C is K2 times concentration of B, no, sorry, not the concentration of C, dc dt. dc dt, you know, look at the last one, dc dt is K2 times B, and the concentration of B actually has become a constant even though it's a small value. So this is concentration of B is a small constant value after some time, multiplied by a large number. K2 is large. Okay. So, that will give you a constant dc dt, and that constant dc dt shows up in this plot in the form of a straight line. So, the slope is constant. Okay. So, basically what this means that after a while, after a little while, when B concentration of B builds up, after a while extra amount of B that is getting produced is getting quickly consumed, that is all. But it is able to maintain its concentration at a low level which is constant, that is a steady state. I was thinking of giving you one practical example, maybe I will just write this very quickly before we close, and we will continue the discussion in the next class with consecutive reactions. So, just to give you a practical example, you can have a nitric oxide system where this happens. All right, and this happens. So, this is like A going to B and B going to C. Why? Because we have this N getting produced here, which is like an intermediate which is getting formed by a first reaction which is typically slow, and this same intermediate gets consumed in the second reaction. So, slow first reaction and fast second reaction. So, this will lead to d dt of N approaching 0, that is N giving you a steady state value. All right. Now, I think we are running out of time because yeah, almost through. So, we will stop here. So, the plan for the next class is that first we will take up from here. I think you have some questions probably still about why B reaches steady state, and what I asked you to do today is maybe you can just take the B expression and plot these two terms as a function of time. So, that will help you visualize, plus we will address that issue from the point of view of this set of reactions of nitric oxide. Okay. That will give you a practical example to work with. So, we will stop here. Thank you.